Okay, welcome to the OpenEXR project update. I'm Cary Phillips, and R&D supervisor at Industrial Light and Magic. I'm going to share a little retrospective of the work that's gone on in the project over the last year, but the main attraction today is Kimball Thurston going over the new 3.1 release and which is the first substantially new functionality to be added to OpenEXR in quite a long time. We're also going to have a discussion around spectral image data in OpenEXR from Alban Fichet. So just to start off with a little context and review the OpenEXR project mission, we are, of course, the keepers of the high dynamic range image format for the motion picture industry. And the guiding principles that we abide by emphasize robustness, reliability, security, compatibility, performance, simplicity, and wide adoption across a broad spectrum of platforms. This is not the kind of project that you expect to see a lot of tremendous amount of churn on. I'd like to introduce the OpenEXR steering committee. Me, Cary, Christina Templar-Leitz from Epic Games, Joseph Goldstone from ARI, Kimball from Weta, Larry Gritz from Sony, Nick Braccino from Pixar, Peter Hillman from Weta, and Rod Bogart from Epic, who was also one of the originators of OpenEXR. You can contact us through our email alias at aswf.io or through Slack or through GitHub issues, and you're welcome to join us for our every other week steering committee meeting. Looking back over the last year, we've put out several patches to OpenEXR 2.4 and 2.5, and we made the release of OpenEXR 3, which we previewed at Open Source Days last year. The general theme of what's gone on in the last year is security, dealing with a variety of issues like buffer overruns, integer overflows, that kind of thing. A whole range of build and CMake improvements. And what OpenEXR 3 represented a major reorganization and modernization of the library. One thing I did want to mention before we go on was what the topic we raised at the Open Source Days last year, a proposal to update OpenEXR's default metadata to be consistent with the ACES container spec. There's not a lot to report on this, except to say that the VES Tech Committee is deciding to take up this banner and is organizing a project around exploring what is the metadata across motion picture production pipelines that is the most important. How can we consolidate consistent names, definitions, units, as well as identify who are the keepers of those standards. Because OpenEXR injects a default set of metadata into files, there's a role for us to play in this, but we're really going to defer to the lead to the VS Tech Committee. If you have ideas or thoughts about this, you can contact them at the email address here, vstechcamerametadata@googlegroups.com. So getting into the heart of the matter, Imath 3.1, thanks to Kimball, has included optimized float to half and half to float conversions using hardware instructions if available. There's also a lookup table free version of the conversion operations that is slower, but also without the lookup tables is appropriate for certain situations where memory is at a premium. And kind of continuing with or leading into something Kimball's going to talk a lot more about, it's accessible in a C language API. So I'm going to hand it off to Kimball now, who will go over the new OpenEXR core library that he has developed, thread-safe non-blocking I/O, and various other features. So take it away, Kimball.
Thank you, Cary. So yeah, so as Cary mentioned, we've been, sort of the first major thing, and we're sort of doing this as a technology preview, and I'll sort of go through a little bit, both the technology sort of as it exists now, and a little bit of, but I thought it would be good to start with a little bit of background. And so if I can hit the right button, one of the issues that that I know we run into is that we have a renderer at Weta called Manuka, and we might be choosing to render this couch, and if you have just a single thread, then you can I'm losing control here. Then you can make the standard sort of file handle calls, and say set frame buffer and read a tile. This is fine. This is great. This is what the OpenEXR API has done for years. But if you have a bunch of threads now, and they're all happen to be because we have a pattern, and it's a lazy programmer art, as such as it is, and I only pulled a small piece of a couch. We might need to repeat that, and so maybe we might be accessing the same tile in a bunch of threads, and if we do that, then right in between here we have this condition where if we were using the same file handle across multiple threads, then we would have a race condition, and one thread could set its frame buffer to read a tile, and another thread could be actually reading the tile at the same time. And so the EXR library has a mutex internally, but even across these calls, that mutex isn't locked across those two calls, and so you end up sort of reading the wrong tile into the wrong frame buffer. And so, sort of diving into that a little bit more, even if we sort of avoid that, one of the issues that once you're starting to micro optimize, if you're trying to do this read tile, well, actually, what's really happening is under the background, you have to read the data from disk, and you have to decompress it, maybe, assuming that you have a compressed EXR, and then you have to sort of unpack it to whatever format that you want. And the way the EXR library provides this, and it's great, served us well for years, but it's really designed around reading full images at once, is that it's got a thread pool, and so it'll read it, and then the unpacking will and decompression will actually dispatch to a second thread behind the scenes, right? And so this causes a bunch of overhead. Now, this might be a little bit of a misleading sort of fake news kind of thing, in the sense that you can, when you construct the file handles, say, hey, don't use any threads. However, the mechanics of this being enabled still means that there's these mutexes in place to ensure safety, and so you still incur quite a bit of overhead in that process. And so, continuing on in the performance vein, one of the other things that happens with the existing EXR library is, as Cary mentioned, we've designed it to be as cross-platform as possible. And so, but when you're reading things such as like the chunk offset table, which is basically the offsets into the file where all the real data lives, it ends up doing that effectively one int64 at a time, right? So you're making an int64 read request for everything for each individual one, and this is largely fine if you assume that you have operating system buffering and such, but there's still a fair amount of overhead. And the other thing about the read is that it's actually doing the byte swapping, the portable way in the sense that it's always doing shifts and ors and the bit masking kind of things. And this is often, if you're just reading something, it can be hidden by disk IO and these other things, but it does add quite a bit of overhead compared to in the C library, we're using pread, and I'll talk a little bit about that in a second, but we can just read the whole block, and then on the hardware where you are in the wrong Indian layout, then it can swap. And so, so as I mentioned, we have made this, or I have made this change, I guess, but we everyone else agreed to it, that you know, the existing library is stream based and basically avoids seeking at all costs, and it even has extra like conditionals to make sure it doesn't make a seek call and all these sorts of things, because when it was written, the seek calls were incredibly expensive. In the new core library, we've sort of flopped that around and said, well, we'll just know the file position and be the file position. And we'll use the operating system's abilities to read without seeking. And on POSIX compliant systems, so under OS 10 and Linux and BSD and all these other ones, you can just use pread. Under the Win32 API, they have to read file, there's an overlapped file IO struct that you can pass in to pass in the offset to the file to read from. And so with that, you can do this without having to seek into the file handle. And so, speaking of reading, what does reading look like in the new OpenEXR 3.1 C API, right? So it's a C API, and we chose to do this. There were a bunch of questions around this, whether to do a C API with a C++ underneath it, or just do whatever, and ended up choosing a pure C API, such that we can link into programs such as FFmpeg, where they choose to keep only the C layer as much as possible. It also I'll talk a little bit about it a little bit later, but we're also sort of, with this C API, able to bind to other languages much more easily. But one of the things that you'll notice about it is that it's designed to be as stateless as possible, and so there are from file handle to file handle, meaning that the library itself stores very little state, and everything is passed through a context, right? And so even starting a read, you can you pass in, when you open a file, you basically pass in any error handlers you want to have, but also you can override even the malloc that the library uses, or pass your own user data in and use a custom read function. But in the end, you basically just make a simple little EXR start read call, and that will not return until it's actually parsed the whole header. And the one thing about that is sort of from a performance, but with the other changes that I talked about a moment ago, where we've changed it such that we're doing these sort of block reads as much as possible, and doing a little bit of read buffering instead of reading one byte at a time. Then we actually have improved the performance of parsing that header from the existing library on, I don't know, it's a CG render, so it's got some metadata in it. It's not a massive amount of metadata, but it's got a representative set from a production set of metadata. In the current library is about 400 microseconds, and the new one is about 55. And so that's, you know, 7x or something. And so that means if you're reading lots of textures, the time actually adds up over over a course of a render. And you'll notice also that every function in the C layer returns a result type, and so it returns an error status, and then passes in an output parameter. And we do this so that we can, well, for consistency, but also for having guaranteed lifetimes of data and the like. So once you've opened the file, the next thing to do is sort of look at some of these attributes. And in the core library, one of the choices made is actually to preserve the attribute order that exists in the file. In the existing C++ layer, it gets loaded into a map. And so that map ends up in basically alphabetical sort order. So it's sort of, if you read and write, you'll end up with things that potentially in a different order. Now, of course, if you're always having things sorted, then it stays the same. But we've done this sort of keeping mouth work. We've done the keeping the attribute order for potential future optimization that we have talked about in the past, where we put important information like the data window always first. This is not yet taken advantage of, but it's in there for us to play with. And then you can, through the C API, query it either in this original file order, or the more traditional sorted order, the way you would get through the C++ layer. And so how do we do that? Well, let's say we want to read we want to query the data window. And so that's fairly easy enough. Dropped away all the return value checks just to sort of make this not a wall of text as much. So assume that I'm checking the error status from each of these. But you can for the required attributes of the XR file, there are functions where you can directly access them, and you don't have to have strings in your code. For an arbitrary attribute, you can pass it in by name and do some access it that way. And so you'll notice that I haven't used the Imath box2i type here. This is just a simple little C struct. It should have, well, it must have the same memory layout as the Imath box2i type. And in fact, it should, with one of the contributions that Larry Gritz put in, where the Imath constructors can do struct-based template expansion. This should you should be able to just construct an Imath box2i type from this transparently, and so that should allow you to use any of the C++ functionality that's in the Imath types, right? So box2i doesn't have so much functionality, but vectors and matrices and those sorts of things, of course, do have a lot of functions, and the C types don't provide any of those functions. They're just data storage. Another thing that you'll notice here is this 0, and that's because I was lazy when I was making these slides, but this is the part number of the file. And so one other thing to say about the C layer is it only presents an API that is for EXR2 and newer, where it's a multi-part file. The one thing to say about that is that if you only have one part, it will still write an EXR1 compatible file. But the whole API is designed around sort of multiple parts. And then one other thing to mention, and this is sort of showing the generic, you can, rather than having to know the names and do that, you can iterate and sort of just peruse what attributes are in the file. I thought I would take this slide to also mention that the C library, just like the rest of EXR, uses all of the import export things. So it's only exposing the API, the public API. So all the other functions are hidden and internal. But then, you can get attribute by index, get attribute by name, and get the attribute list and sort of query your attributes there. And I suggest you look at the Docshin documents that sort of describe these things. The one thing to note is that we have put in sort of the ability to register custom attribute type handlers. So if you have a custom attribute type, such as maybe what Alban will talk about in a little while, then you can actually register a handler, and then the library will use that handler to automatically convert for you when you query these things. Some of this is sort of experimental, and we're looking for feedback on that. So if you do play with this and you find a deficiency, don't be afraid to file a bug or an issue. So continuing on, attributes and files are interesting, but what we really care about is getting at the data. And so how do we do that? And so a new thing that is exposed in the C layer is what I'm calling a pipeline here. And it's really just a generic abstraction around the process of accessing the data from the file. And we've done this so that we can enable things like using the EXR library to read data from the file and maybe to decompress it, because sometimes that's complicated, but then you might in the middle upload that to the GPU and do the unpacking on the GPU, because that's a lot faster. One of the other principles is that it tries to pass through your memory into the reader as much as possible. And so one of the distinctions between the C and the C++ API is that there's no caching. And so if you have a file that is compressed with the 16 scanline zip mode, and you ask for only a single scan line, you have to read all 16 scan lines. And so in that way, this is trying to be as close to zero copy as it can be. Obviously, it's only ish. The other thing to note about what I'll talk about in a second is that these pipelines can be reused to avoid any reallocations, which sometimes allocating buffers on the GPU can be slow. So you might want to not do that all the time. So as I mentioned, it's a pipeline. And so what does that pipeline do? Well, for all of you that use Nuke, this will be the simplest node graph you've seen in years. There's for reading, there's really only four things. One is read the data. Two is decompress if it's compressed. Three, there's a step in here to allow you to realloc based on what kind of deep data there is, and then if you have a deep file or deep part, and then finally a step to unpack and convert into whatever format that you so choose. And one of the features is that it can, rather than blindly going through this, it will skip some of these steps if it can, right? And so if you are reading an uncompressed file that's in the same layout that you want, it'll actually bypass all of this and just read straight into your memory. Again, getting as much towards that zero copy state as we can. Okay, so pictures are nice, but code really speaks volumes. And so what does this look like in code? And so as I mentioned, this is an example of reading a scanline file. So you can say, hey, how many scan lines are there per chunk of data? And the term chunk is used in the API here because that's what the term was that was used in the technical file layout document, which Cary has converted to restructured text, and so is included in the read the docs page now. So thanks to Cary for that. But anyway, they use the term chunk, and so I've kept that. But a chunk is basically the atomic unit that you can read at a time of data from the file, and that can have different forms depending on the compression that's used for that part. And so you might say, okay, how many scan lines are there per this chunk? And then I'm gonna loop over the data window and read those in. And so you ask the you ask the file for the information for that chunk, and then you can initialize the decoder with this decoder pipeline that I talked about with that chunk info. And what that's doing is basically it populates a data structure with the channel information for you and a bunch of other things, and then you can go through and give the decoder the pointers to your memory, right? And we're, again, as a reminder, we're doing this all to be as stateless as possible. And I didn't show it here, but you can also request that it convert from half to float or other conversions. But then once you've done that and you've given it the strides and the line strides, you can also, at this point, populate the decoder with your own functions if you're doing something clever like GPU unpacking, or you can just use the default routines. And we have you do this afterwards such that it can look at the strides that you've specified and choose a more optimal unpacking routine, such that if you're going to interleave from planar or vice versa, it can do more optimal unpacking. And then finally, the interesting bit is you run the decoder, and then in theory, minus bugs, that you should have the image data in the pointer that you gave to the library. And so finally, one other thing, you'll notice that I had the initialize in there, and there was also, actually, if I go back, I had this commented out thing saying update. One other pattern you can do is you can initialize once. And in fact, this code kind of has a bug because I didn't put the destroy inside the loop. But one thing you can do is the first time you set up the decoder, you can initialize that, and then the subsequent ones you can just update. And that's sort of a lighter weight. It doesn't reallocate a channel structure or anything like that. And so you can just very quickly update based on the new scan line that you're going to be reading. And then you don't have to if you're just reading into the same layout, you also don't have to go through the process of it figuring out what routines you're going to use and whatnot. So you can kind of skip that. But anyway, once you're finished decoding, then you of course need to destroy, and this actually frees up the memory, right? And so, as I mentioned, we'll cache the memory pointers in that decoder struct so that you can avoid reallocations in your inner loops. And then finally, when you're finished with a file, you just sort of say EXR finish, and that will shut down the file context. So that's reading. What does writing look like? Writing is really just a mirror of reading. The API is all very consistent, and I won't bore you guys with those details. But it's basically you set up the inverse structure and the inverse pipeline where you're converting, compressing. There's this yield for sequencing such that you can actually do the compressing and converting in parallel if you so choose. That's up to you. But then you can block and wait for it to be the right order, because some EXR files have a strict ordering for scan line ordering. And then finally, of course, you write it to disk. Some notes about this. So why have we done this? So this removes all of the threading overhead and makes the caller responsible for any of that. The only sort of halfway threading thing that's in in here is during writing, there is a mutex that is used to ensure that you're writing things such that it doesn't produce a corrupt file, in terms of making sure that things are happening in the right order. But during reading, there's absolutely no mutices. There is an atomic swap of a memory pointer for the chunk offset table so that it can lazily read that chunk, because that can be somewhat larger. So if you're not accessing a part, you don't have to incur the cost of reading the chunk table for it. And so yeah, so there's no hidden data, there's no cache, as I mentioned, and no mutices. It does assume this use case for this overlapped IO, this pre-read IO, and so this may be not such a good idea for cloud storage or things like that, but I don't think that that's a use case the library should necessarily design for. And I think that because the IO is customizable, you could actually produce a memory, obviously a memory stash of something where you have cloud storage. But I just thought I would mention it for anybody who is looking at doing that sort of thing, would be interested in hearing feedback around that. And I saw a question go by that I think got answered. This API is currently purely additive. All we've done in 3.1 and why it's only 3.1 is that we've just added this C API as a technology preview to sort of try to get feedback from people who are interested in the GPU unpacking, or in tuning performance for the texturing system in their renderer. And so we're sort of looking for feedback, and the next sort of steps that we have, there's a couple of corner cases that didn't get finished before release. One of those is the DWA compression types. It can read and write the compressed data fine. That's not an issue. But if you have a file with this, you would have to do that custom pipeline decoder that I was talking about, and call the C++ versions of the decompression routines currently. And finally, some of the deep packing stuff didn't make it in the release. So the writing of a deep file, you may have to do a little bit more work to pack the data into the file format. But those will come along fairly soon. And so yeah, so if anybody can help with the testing this sort of idea of whether this decoding pipeline is worthwhile and helps, that would be super amazing. But then the next step is to start replacing the internals of the C++ library. And so we think this is going to represent a fairly noticeable change to the ABI, meaning the structure layouts will change. And so we might have to change this to a 4.0, EXR 4.0. We haven't decided that yet. And then we will be adding API to the classes at least, so that, and we haven't yet decided whether we'll deprecate that sort of pair of set frame buffer and read pixels yet, or not. But at the very least, we'll add API where you can do that in one step, and get at the data in an atomic fashion, such that you can avoid the thread issue there that I talked about. So one final thing I should mention is that, so we've done this and designed this API such that it's compatible with things like Rust, where Rust has a very, very strong concept of mutability and data lifetimes, and so that was sort of one of the design goals, was to be compatible with these sorts of languages, such that they can bind in and use the library and feel confident that they're doing so safely. And so if there's any places where anyone discovers that this isn't true, then please let us know immediately. But the one thing that I should mention is that the Rust project also has at the same time concurrently made a new tool that can provide Rust bindings for C++. And so, and in fact, it's not even just for the XR project, they're doing it generically, and they'll do it across all of the ASWF projects here in relatively short order. But they started with OpenEXR, and so there'll be a process over the next wee while where you see us adopt those Rust bindings and expose that language. And so with that, I think I will end my portion of the talk and hand over to Alban to carry on, and please continue to ask questions or anything like that. But take it away, Alban.
Thank you, Kimball. So hello, everyone. So I'm going to present the work we've done with Roman Pakanowski and Alexander Wilkie on how to store spectral images with OpenEXR. So with this presentation, we hope to get feedbacks about the format and potential future regions, and we want mainly to have a common exchange format for spectral images. So first, let me briefly introduce the link between spectra and colors. So light is an electromagnetic wave, and the radiation can be represented by a spectrum. And when bouncing on different surfaces, the spectrum will be attenuated and then captured by your eyes or by a photographic sensor. I won't go much into the details, but basically a camera sensor eyes have 3 types of receptors capturing different parts of the spectrum and interpreting those as colors. A spectral renderer, contrary to its RGB counterpart, basically transports and attenuates spectra instead of colors, and this provides much more accurate results in terms of color accuracy, as you can see in the image here. It's the same scene, but rendered with 2 different rendering methods. And this is especially important when you want to mix real footage with CGI scenes. Now, the output of a spectral renderer is a spectral image, to be precise, an emissive spectral image. And this has several advantages over traditional RGB image. First of all, it is observer independent, which means that the image can always be recalibrated for a specific observer instead of relying on the average observer. Second, it is display independent, and the spectral information can be represented in any color space with a high degree of accuracy instead of relying on approximative color transformations. But the interest for spectral images is not only for the output of a spectral renderer. Such type of rendering systems really need spectral information to exploit their full potential. So for instance, a spectral image can be used as a reflective texture, and then it stores a reflective spectrum per pixel. But it also can be used to lit a scene. Then a spectral image can be, for instance, a norm map storing for each pixel an emissive spectrum. And you understand there that having a common exchange format for spectral images is highly desirable to allow exchange between different software. Now let me show you how we pack those kind of spectral information in OpenEXR. We extensively use the layering system of OpenEXR to store multiple frame buffers in the same file. So for emissive image, we have a S0 layer hierarchy, having child layer for each of the wavelengths, representing then the emissive spectrum for 1 pixel. An emissive image can also be polarized. Then, in such case, we add S1, S2, and S3 layer hierarchies to store the individual components of a Stokes vector per pixel per wavelength. For reflective images, we store the T-layer hierarchy in the same fashion, representing the reflective spectrum. But we also can use the flexibility of the OpenEXR format to allow storage of fluorescent textures. This is a very special kind of reflectance, absorbing energy at a given wavelength and re-emitting it at other wavelengths. Then we build a hierarchy for each wavelength to store a full radiation matrix per pixel. Now I'm going to show you why we found OpenEXR to be the perfect choice for this type of weird format, I would say. It's not only because it is widely used in the CGI community, but we also can make our spectral format backward compatible somehow. in quotes, with RGB compliant, with RGB OpenEXR compliant software. So let me give you an example here. So if we open the image we've crafted before in our specialized software called Spectral Viewer, obviously all the spectral information are accessible. But now, if we add additional RG and B layers, we can make this same file readable by any OpenEXR compliant software. Here, for instance, with GIMP, Photoshop, or the macOS image viewer. And I stress on that, but that's the very same file. And this allows to have a fast preview of the spectral image, even with software which does support only RGB OpenEXR images. And we can even use this same image in a RGB renderer. Such non-spectral aware software would just ignore the additional spectral information in the file. Additionally, the OpenEXR format allows to store additional metadata, which is handy in our case. In our specification, we propose ways to store additional information about the camera spectral response, each layer spectral response as well, radiometric units, and layout revisions for future improvements, to name just few of the metadata we store. So if you want more details about the specification, please read our published article in JCGT. The link is in the QR code. I want to thank the OpenEXR developers for providing really meaningful results during the development of the format and for inviting me in this talk. If you have any suggestions for future revision of the format, I would be highly interested to hear those. So that's all for me. Thank you very much.
Right, so I guess we have a little bit of time for general Q&A and discussion, right, Cary? That's the...
Yes, if anybody has any questions, there's a couple questions.
I'd like to reiterate 2 questions that I answered in text, but just in case anyone isn't following that. Someone asked whether the changes that Kimball mentioned are already in the main branch of the repo. They are in the main branch, and they're also released as the new OpenEXR 3.1. Previous caveats apply about the couple of corners in which it's incomplete. And also in the current master of OpenImageIO, there is a build time flag that will switch the EXR reader in that package to use the C interface. The hopes being that that will be a way to explore the new performance benefits. But you have to turn that on, but that will be in OpenImageIO 2.3. Another question is, Kimball partly answered, but I'd like to underline it again. The release 3.1 adds the C API. It does not change the C++ API. The plan for 3.2 and going forward is to migrate the internals of the C++ API to use the new core library underneath. So the C++ API will migrate to having that kind of performance. Fully getting to that performance will probably require adding some new API calls to the C++ side. We don't know yet if it'll break back compatibility in such a way that we'll have to rev all the way to 4. I think that hasn't been written yet. As far as the open question, there is an interesting one. But one disappeared. Spectral.
I think Alban answered it.
Yes.
About spectral viewer, he had the link
to the URL of a spectral viewer. That's cool. Look in the answered Q&A for that. Bill asks, are all the layers in one channel? And for spectral imaging, or is it using the color channels in some way other than independent parts of the color? So that's a question for Alban.
Yeah, so basically each each OpenEXR like frame buffers or layers, each of them stores an individual black and white image of the specific wavelengths you're looking for. And we use dot as enforced in the OpenEXR recommendation to describe a hierarchy. So that's why when I'm saying it's a S0 layer hierarchy, it's just S0 dot prefix in each of those type of emissive spectrum, for instance. So each of those layers are individual frame buffer in an image, which also you can prefix, for instance, left or right to have stereo spectral image, or you can use the same. We don't make any assumption about using multi-part EXR, for instance. So you can definitely also have a multi-part EXR, which each individual part is a spectral image. I hope
and
that's a question.
you didn't talk about this too much, Alban, but one of the things you have a header entry to sort of describe what the spectral layout is. I mean, we have talked about doing a different a custom attribute type for that as well, but
yeah, that's just like a first iteration of the format. So
Yeah.
obviously there is a lot of things that, for instance, like the attributes we store for the camera response and stuff like that are basically strings, formatted strings, because we wanted to make it kind of available right now, without trying to add specific types, which would imply using a specific library to open those type of special OpenEXR files. Here you can just use OpenEXR library and read those things. You just will have to parse those kind of strings, which is not very elegant, but at least it works for now.
so there's another question from Mark. Do you have a mechanism to assist where you may have wavelength samples at different frequencies, e.g. 10 nanometers for some images or 1 nanometer for others?
Yeah, we don't enforce anything about spacing the layers. You can even have heterogeneous sampling over the spectrum. You just parse the name of the layers, and I mean, there is something you can definitely screw the thing up, because you can specify a filter according to that specific layer, which is absolutely not in the same range. But well, to make the thing kind of simple and user friendly, you just have to specify in a special format the name of the layer, which gives then the expected response for that specific wavelength, and then you can add as many as you want. And you can also have a non-homogeneous, I would say, non-regular sampling over the spectrum. And if you don't specify the layer response, the filter for each of the layer, we specify in the paper what should be expected in such kind of irregular, especially in such kind of irregular sampling, where the wavelengths indicated in the layer name doesn't necessarily mean it's in the center of the captured frame.
I'll also recommend that people interested really look at the JCGT paper, which lays a lot of this out in great detail. It's really interesting.
Well, if there's no further questions, we can maybe call it a day. As just to follow up on what Kimball has said, I think, you know, over the next few weeks, months, we'd really like to hear feedback about people's experience with the new library. And, you know, as that functionality is validated, we'll proceed with replacing the core of the existing API with the new functionality, and put out releases as soon as we're confident in that behavior. Okay.
We should also mention that if all goes well, we are expecting OpenEXR 3.1 to be the 2022 VFX reference platform standard. So it's a good time to start doing builds, making sure your downstream applications are working well against 3.1, especially if you're currently building against 2.4 or worse, and there's a little bit of conversion to do. And so we encourage people to get their ducks in a row. So that's a smooth transition for them.
And the porting guide has some help in the kinds of changes that you need to make, as well as a little bit of advice in how to support both 3 and 2 simultaneously.
So there's one question that popped in. When do you expect the DWA star compression support in the C API? So that one is just, there's a large swath of C++ code that I didn't want to copy and port over. And so to have it be C only. And so that can happen in fairly short order, and it doesn't represent any sort of change in the API or anything like that. So can happen as a patch release, and so we might do that as soon as we can. Maybe the next month or so, we'll get to that, along with the packing of the packing mode that I mentioned for deep that doesn't quite work. But yeah, I expect that to be in fairly short order, and we'll probably put that out as a patch release.
Well, if there's no further questions, why don't we conclude with that? Thank you for attending, and let us know your feedback.
Thanks all.